Hello, and welcome to the Irrotational Flow module. I'm John Borg, a faculty member here at Marquette University. And we're going to start today by just going over some of the basics of what irrotational flow is and how we can use it. So irrotational flow is a subset of this set of equations here. This is the conservation of mass, momentum, and energy, and we can make this applicable for a fluid by inserting the right shear stress relationship here. We'll do that later. But these are the overall governing equations, and due to various nonlinearities, we can't solve this equation. There's a nonlinear term there. There could be nonlinearity within the shear stress term, and there's a nonlinearity within the conservation of energy with regard to the convective terms. So these terms don't have a closed form solution, or this set of equations. So one of the things that we can do is make some simplifying assumptions and get some baseline solutions. So we'll talk about that, and that really forms the overall crux of what this module is about. So this module, the objective is to introduce you to irrotational flow and what those solutions are. And then from those flow fields, we can make estimates of the full velocity field and then convert that to a pressure field using the Bernoulli equation. Some of the basics that we're going to do in the module is just define the nomenclature for irrotational flow, and then I'm going to show you how we derive the Laplace equations using the definition of a stream function and a potential function. Then we're going to seek some basic solutions to the Laplace equation, what I like to call the building block solutions. And then from these, we can build up to more complicated solutions, such as a flow over a sphere. And then we'll go over some examples in all of this, and I will show you how to convert these flow fields into pressure fields using the velocity profile. And then we're going to end the module with a bit of a numeric exercise. So the module ends with a numeric exercise for flow over a forward-facing step. All right, so the assumed skills are that you've had some introductory course in fluid mechanics, and that would really mean that you're familiar with the Rayleigh transport equations, basically conservation of mass, momentum, and energy in integral form, as opposed to the differential form, which I showed you earlier 2 slides ago. So those earlier slide, that was the Navier-Stokes equations in differential form. The student should be comfortable with vector calculus. We're going to be doing a lot of vector work with derivatives and partial derivatives, so you should be familiar with that or comfortable there. And maybe a working knowledge of the partial would be good, but I think I'll cover that kind of from the basics, so maybe you can follow along. And then ultimately some proficiency with computers. I think that most students are pretty efficient with MATLAB, and so that's a good starting point, but hopefully I can encourage you to learn a programming language such as C or Fortran, a compilable language that is much faster. All right, so let's get started. What is in a name? Well, this module I termed irrotational flow, but you'll see people use a lot of different names. One of them is inviscid flow. So in an inviscid flow, we assume that the viscosity is 0, and in so doing, we simplify this set of equations here. This term goes to 0. And so that's pretty nice. And that gets rid of the nonlinearity. And so as a result, you can get closed-form solutions. Another term that is used is ideal flow. And this is a nice name, but it's maybe too general, right? So ideal flow can mean a lot of things to a lot of different people. In general, people agree that it means inviscid, but it also makes some implications about whether this is a gas and ideal gas assumptions and things. So we want to keep it general, as we mentioned, to fluids. And so I don't necessarily care for the ideal flow. And neither ideal flow or In viscid flow, they both assume that the viscosity is zero, and that's really not what we're doing in irrotational flow. We can do all the stuff in this module without having to assume that the viscosity is zero. So I prefer to use the term irrotational flow. I think it's more descriptive. I think it's more exact as to what it is. It implies that the rotation is zero, that the vorticity is zero. This is kind of a new terms to a lot of students, so it's not as accessible, but it is the more exact term. So I'm going to use irrotational flow to describe what we're doing here. Some people call this potential flow, and really that comes from the fact that the orthogonal function to the stream function is called the potential function. So that's a lot, and I think that it's a little bit too descriptive or just a little bit too nebulous as to what it means. So it's correct, but it's not really what we're doing. So all of these labels you'll see, if you're Googling around or you're looking in textbooks, you'll see that what we're talking about is these names are used for all of what we're talking about. All right, as you can see, I love books, and I do like to read a lot of books about mathematics and fluid mechanics and thermodynamics. So I thought I'd go over some of my favorites that cover this topic. This book right here, this is Kundu's book, and this is an excellent textbook for advanced fluid mechanics. It goes over things in much more detail than you would find in a typical undergraduate book, sometimes maybe even in too much detail, so it's not necessarily the first place you would look, but it does things like time-varying irrotational flow, which is not covered in a typical undergraduate textbook. Kundu decided to use the term ideal flow as the chapter title for this section. That's fine. And this book has been around a while. This is the 5th edition. I think it's in the 6th edition now, and but pretty much since the 1st edition, it's been a great book. The next book that I really like is Frank White's book. So Frank White has had this book out for many years. This is the book I used as an undergraduate, and it is currently in the 8th or 9th edition, and it goes back many years, as I said. And so the upside is that it's very accessible. You can find these even 2nd, 3rd editions for pretty cheap on the internet, and it hasn't changed that much. You can use the 4th edition and compare it to the 9th edition, and it's almost page for page exactly the same thing. I really like this book because he covers it in what I feel like is the perfect depth for an undergraduate student. So it's very readable, but it doesn't go on and on and on. He entitled his chapter Potential Flow. So you can see that various authors are using different names. This is a really great book. This is the Fox McDonald book, and they have added Pritchard as an author on this book. And this book goes into a bit more detail than Frank White's book. I would say it's somewhere between Kundu and Frank White's book as far as the depth that it goes into. They title this Viscid Flow. And you can see that they take it really from a differential equations point of view. So that's why I say it's a little bit more in depth than Frank White's book. And there's a few other books that I don't have copies of that I like. There's a newish book by Sengal. I think it's in its 3rd or 4th edition, and I would say it's probably it's very readable, but it doesn't go into the depth that Fox McDonald or Kundu does. And also, I would be remiss if I didn't give a shout out to my PhD advisor, Robert Kirchhoff, who wrote his own book on potential flow theory. And it really focuses on computer graphics solutions. So there's a lot of plots of what these potential flow solutions look like. So it's a nice book, and it is in our library. So let's talk about irrotational flow. This is an image of a real flow field. Here's an airfoil, and it's a real flow field in the sense that there's a boundary layer that grows as a result of the no-slip boundary condition. So within this boundary layer, we term that flow the viscid region. So those particles are being acted upon with a high degree of viscosity. And outside of the boundary layer, the flow really doesn't know that, that there is any viscosity. It's really the inviscid outer region. And so you can think of any flow over an external body as a viscid region near the body where vorticity is generated, and then outside the body there is a region where vorticity is not generated. It's the irrotational region. And so what we tend to do is think of these two as competing or complementary types of flow solutions. So really what we're going to do is focus on this irrotational part. And the boundary layer tends to be quite thin and small, although extremely important. So what we're doing in this class is we're replacing this real boundary layer phenomena with just the pure inviscid flow. So you can see I've just kind of translated this velocity field down onto the body. This will give us a great first approximation of what the flow is, and I would say up until computers really took their own sort of life, people thought that what we could do is solve the irrotational flow and then solve the inviscid, the viscid flow, and then marry the two together using matched asymptotic expansions. I don't think that that's being developed as much as it was in the 70s and the 80s, but computers have really taken the approach that we'll just do the whole flow field. So, but it is an interesting, it does result in a lot of interesting analytic solutions. All right, so what's the basic maths in this module? The basic math is the Laplace equation. So here's the Laplace equation, del squared psi is equal to 0. And that's a linear equation. You can see it's a homogeneous linear second order equation. And because it's linear, it means that any solution to this equation can be added to any other solution to form a third solution. And this phenomenon is called superposition. So Laplace equation is subject to superposition. So we could find a solution such as the linear uniform flow, parallel flow. Another solution would be a source and a sink. And so another solution would be a vortex. And these are what I term the basic flows. And so using these basic flows, what we're going to do is combine them together to make more complicated flows. So here's an example of doing that. This is flow over kind of a blunt nose. And in general, this is called the Rankine half-body problem. So here's the body right here. And what we have is we have the flow comes in and it stagnates onto the leading edge of the body. So we have a single stagnation line. But the majority of the flow goes up and around and over the body. So what we're interested in maybe doing is modeling this exterior flow as an irrotational flow, so neglecting the boundary layer effects. So this is an experiment that was done in a wind tunnel, but I could impose a free stream on this flow and a point source, and together the Laplace equation would yield a full-up solution like this. So this is an approximation of what the streamlines look like. So you can see it does a fairly decent job in capturing the leading edge, and you can see the streamlines therein. So if I separate these out, you can see that really what I have is this irrotational flow solution and the experiment. You can imagine that the body is in there. You know, really, when you do the irrotational flow solution, you get the full solution everywhere. And so within the body, there's a flow. And if I was interested in, say, this particular flow, which might be something like a river coming down and the emission of a waste stream or a pipe being submerged into that river, and thinking about how all of that flow field works together, this would be an approximation for that. So one of the characteristics of inviscid flow theory is that one solution can represent many solutions. Another example is that for any streamline, we'll cover this next time, any streamline itself could represent the body. So it's arbitrary that I pick this to be the body. In fact, I could pick this streamline to be the body if I wanted to. So that's just a characteristic of irrotational flows. So we pick that to be the body, and we think about the exterior flow around that. From this streamline, I can calculate what the full velocity vector field is, and it would look something like this. And then in addition, I could calculate what the pressure on the body is, and this is helpful when calculating the forces on the body. So you can see that it really is quite a powerful technique. We can calculate the flow fields, we can calculate the velocity vector field, we can calculate the pressure field, which ultimately means we can calculate forces. So keep in mind that these are simple solutions. They don't capture all the flow field, they don't capture the boundary layer specifically. The viscous effects are lost, but the sense of the field is captured, and the relationship between the velocity and the pressure is captured, which a lot of times is very important. All right, so I think we went over everything here with regard to introducing irrotational flow, and we covered these topics. And next time, we're going to go over streamlines, streak lines, and path lines, and start the derivation for what is a streamline mathematically. So until then, we will see you next time.